All right, it says recording now. All right, that's better, huh? Okay, so I spent last week talking about the equilibria of a one-component system, and we saw that we had three phases that one component would be in: the solid, the liquid, and the gas. And we looked at how changes in temperature and pressure drove the system between those phases. We saw that high temperature ended up favoring the more dispersed phases, so the gas phase and the liquid phase, and that the solid phase was most favorable at low temperature. We looked at pressure effects, and we saw that the higher the pressure was, the more favorable the condensed phases were. So we had that at high pressure, the solid phase was generally most favorable, except in the case of water, where at high pressure, the liquid phase of water was most favorable. And the gas phase was the least favorable at high pressure and most favorable at low pressure. And we made arguments for those observations using the chemical potentials. We wrote out how chemical potential changes with temperature and pressure, and we were able to kind of determine mathematically that those conditions would exist. Today what we're going to do is we're going to extend that argument to mixtures, and so we're going to change our number of components from 1 to 2. So instead of dealing with simply one kind of matter, we're going to be looking at mixtures of solutions. And it'll probably be good to go review in your book the different terms that we use to talk about solutions. We have concentration terms. You're familiar with molarity, which is number of moles of a solute dissolved in a solvent per liter of that solvent. Usually we're looking at water solutions, so it's moles per liter of water. There's also units of molality, which is number of moles per kilogram. So it's basically just different ways of communicating how much of one substance is dissolved in another. Your book touches on the concept of molar volume, partial molar volume. We should talk about that real quick. That's an important one. The molar volume is defined to be the amount of space that a mole of a substance occupies in a given set of conditions, right? And so if you know how much volume a component occupies under a given set of conditions, and you know how many moles of that substance you have, then theoretically you can sum up the molar volume of each of the components and add them together, and you'll get the total volume of the system, right? Let me ask you a question. And the question is, would you expect the molar volume of a substance to be the same independent of what solution it's in? Let's say we're talking about a solute, and we said that a particular solute, maybe it's sodium chloride, has a particular molar volume in water. Would you expect its molar volume to be the same in water as you would expect it to be in maybe a liquid ammonia solution or something like that, whatever. So this is the key thing that I want you guys to take home about molar volume, is that the volume that something occupies depends on its exact environment. And if you take something like a sodium ion and you stick it in a water solution, you're going to have water molecules orienting their dipoles around it in some particular fashion. I forget how many waters of solvation, maybe I never knew, the sodium ion has, but the waters will surround it and they'll pull in to some average distance around the ion, and that group will occupy some particular volume in space, right? If you take the same sodium ion, you stick it in an ammonia solution, there's naturally going to be a difference in the electrostatic attractions between the two species, right? There's going to be a difference between the forces between sodium and oxygen, or the water and the oxygen, and the sodium and the nitrogen in the ammonia molecule. And so the volume occupied by a substance will depend on the particular solution that it's in. The molar volume will change. And we're going to take this a step further. Not only will the volume depend on the particular solution that it's in, but it will also, maybe not greatly, but to some extent, it will depend on the concentration of the solution that it's in. So the molar volume of the sodium ion in a 1 molar solution is probably going to differ by some amount, well certainly it's going to differ by some amount, from the molar volume of sodium in a 10 molar solution. So you put a sodium ion in a 1 molar sodium ion solution, it's going to have a particular molar volume. You change the composition of the solution, and you're effectively changing the kind of electrostatic environment of the volume, or of the material. And so the molar volume will change. So it's important for you guys to remember that this term molar volume that we're going to be using throughout chapter 6 and maybe chapter 7 is dependent on the specific environment of the solution that you have. And the specific environment changes from one solution to another, and it changes with composition of solution, right? But if you have the molar volume, and you know the molar volume, then you can calculate it by saying that the total volume of the solution is going to be, if it's a 2-component solution, the number of moles of component A times the molar volume of component A plus the number of moles of component B times the molar volume of component B. Right? We have another thing that we need to think about, and that's called the partial molar Gibbs free energy. We introduced this concept, I called it mu last week in lecture, maybe the week before, and this is just the Gibbs free energy per mole of a component in a solution. And this is going to behave in a way that's very similar to the molar volume, in that the Gibbs free energy of a component is going to depend on the exact environment that that component's in. So the Gibbs free energy of a sodium ion in an aqueous solution is going to be different than the Gibbs free energy of a sodium ion in an ammonia solution. The Gibbs free energy of a sodium ion in a 1 molar aqueous solution is going to be different than the Gibbs free energy of a sodium ion in a 10 molar solution, right? So the Gibbs free energy you can think of as relating the amount of energy that it takes to move a particle from one situation into another, and that's going to be the delta G, the change in the Gibbs free energy, and the amount of energy change is going to depend on the specifics of the solution, right? I'm trying to think of an example to give you for why the Gibbs free energy of a substance would change from one solution to another. Get into this now or get into this later. Let's say we're taking a sodium ion and we're moving it from one phase into a solvated phase where it goes into solution, right? And when we go into solution, so we can just use this example here, there are electrostatic energy changes that are associated with the solvation effects, right? When an ion moves into solution, a positively charged ion, if that solution is composed of polar molecules, those polar molecules are going to orient their dipoles and they're going to try to make close contact of charges. And we saw how energy is released when two oppositely charged species approach. And so if you move a sodium ion into a solution of water, there's going to be some kind of electrostatic energy change associated with moving it there. And if you move that same sodium ion into an ammonia solution, the magnitude of that energy change is going to be different, simply because the electrostatic effects are different in the two solutions. So partial molar Gibbs free energy depends on the exact environment, but if you know it, if you know mu, you can sum the total Gibbs free energy, or you can multiply the number of moles times the partial molar free energies, and sum for each component and get the total Gibbs free energy. So this is an equation that we already kind of talked about. I want to reiterate it real quick. This is addressing the Gibbs free energy of a gas in a particular at a particular pressure. And we saw earlier that dG is equal to VdP minus SdT. And so at a constant temperature, the Gibbs free energy of the gas depends on its pressure, right? You can go back to the previous lectures and look at this calculation, but we found that the Gibbs free energy of a gas at a particular pressure, is equal to G naught plus RT times the natural log of the final pressure over the initial pressure, right? Simply because dG is proportional to VdP. So we set up the integral for dG and look at the changes. If standard pressure is defined to be 1 atmosphere, this equation changes to this form, where you have that the Gibbs free energy of a gas is equal to, or the partial molar Gibbs free energy is mu naught plus that RT line P correction, but instead of P final over P initial, since P initial is equal to 1, we just have P final. We're going to use this relationship here in a moment because we're going to find out that we use the Gibbs free energy of a gas-based species to relate the Gibbs free energy of a species in solution. So a real quick piece of math. We're going to find that for most of the problems that we're looking at, the Gibbs free energy of mixing is negative, and that this applies to both the mixing of gases and the mixing of solutions. So if you take a gas, or two gas species, and you allow them to, say they're separated by some partition, this, if you remove that partition, they spontaneously kind of mix together and occupy the volume in a uniform distribution. And using the relationship that we just saw for the Gibbs free energy of a gas-phase species, we can run a quick calculation to see what delta G is for the mixing of gas, of two gases. So I need to cover that. second. There might be one little piece of logic that I need to throw at you before I do this. There is another piece of logic I should throw in here real quick. We're going to talk about it again in a second. Dalton had a law of partial pressures, and Dalton said, you have another slide here. Dalton said that the pressure exerted by an ideal gas in an environment. Oh wait, I don't need to use this yet. Are you confused now? Yeah, actually I don't need to use this one yet because we're not talking about solutions. Sorry. Okay, you can hate me, that's all right. Well, I'll show you what I was getting at here in a second. So the Gibbs free energy of a gas species, if you look at the pressure that each of these gases exert when they move from one volume to another, the final pressure that they exert is going to be proportional to their mole fraction in the final volume. And so if we have that equation that says the Gibbs free energy is equal to, or the partial molar Gibbs free energy is mu naught plus RT line pressure over P naught, then your final pressure moving from this state to this state is going to be your mole fraction times whatever that initial pressure was. We're finding this to be the two species starting off at an equal pressure, and then once the divider is removed, they stay at that same pressure. So pressure is constant, total pressure is constant. We move from here to here, but the pressure exerted by the gas species changes according to its mole fraction. And so your initial Gibbs free energy of each of these species before they mix is equal to the number of moles times the mu standard plus RT line P, where P is whatever initial pressure these guys started. As they go from that state to this state, their pressures drop, and they end up being the mole fraction times whatever that P initial was. So we have the G initial is number of moles, mu A, RT line P, where P is the initial pressure we start at. We have the G final is the number of moles times chemical potential naught plus RT times line of the P that the pressure that the component exerts at the final stage. At the final stage, its pressure is the initial pressure times the mole fraction. And so G final is equal to this guy here. We subtract G initial from G final, cancel all the terms that are equivalent, and we end up with an equation that says that delta G is nRT times the mole fraction times the natural log of the mole fraction for each component. So we take nRT, multiply it by the mole fraction times the natural log of the mole fraction, and that gives us our delta G for the mixing process. Does this equation look familiar to you at all from any of the previous stuff that we've done? We didn't actually do a homework problem on this, but I think we might have done an example in class where we looked at the expansion of a gas when it moves from one volume to another volume, and we found out that the delta S for that transition was a function of the initial pressure and the final pressure. And I don't know if we derived it, but you can express those initial pressures and final pressures like we did here in terms of the mole fractions. What I'm getting at is that this is, in this model, this term is equal to negative T delta S for our system. The system that we've modeled here is an ideal gas system. The molecules, the particles, don't exert forces on each other because they're ideal gases. And so the delta G, which is equal to delta H minus T delta S, becomes a function only of the entropy change. And so this term we have, nRT times the mole fractions, is essentially equal to negative T delta S. This effect is important. The same delta G, the same form of delta G, is found when we run a calculation on the mixing of an ideal solution. Why is delta H 0 for the mixing of an ideal gas? What's delta H? There's a change in energy. Oh.
There's no interactions between molecules.
Delta H is equal to Q what? QP, right? So if we have a constant pressure process, the delta H is the magnitude of the heat that's changed, it's transferred in a process. When you have an ideal gas, well, let's just use this up here. When you have an ideal gas, these molecules aren't in there, right? And so breaking them from the interactions that they aren't having here and introducing new interactions that they're not having here requires no change in energy. For a real gas, these species are connected by some kind of attractive forces or repulsive forces or whatever the forces are. And so if you remove this barrier, these interactions have to loosen, break, and then the XY interactions have to form. And this is essentially an electrostatic effect. You can think of it as being an electrostatic effect. If the two XX gas molecules are less attracted than the XY molecules, if the XY molecules make a tighter bond, then when we move from an interaction where an X is bound to an X to an interaction where an X is bound to a Y, what's the change in the electric field energy? Is energy released or absorbed? It's released. So we said that when you have charges that move towards each other, they're at some separation and they move towards each other, that electric potential energy is released. And that's field energy. It gets released as radiation or light or whatever it is, right? And so effectively, if you have two molecules that aren't bound very tightly, and you break that bond and you form a bond where the molecules are bound tightly, effectively what you've done is you've taken charges that were separated and moved them together. It's different charges, but effectively in the bulk, in the entirety of the solution, you've moved negative charge towards positive charge. And so you've released a bunch of electromagnetic energy, right? That electromagnetic energy is manifested as heat in the reaction. For an ideal gas that doesn't have differences in the attractive forces between the species, there's no difference between the forces felt between these two molecules and the forces felt between those two molecules. And so when you break this interaction and then you form this interaction, you break even. And there's no heat associated, there's no energy released as heat for that process, right? So in that case, delta H is 0. And so the entirety of the delta G, the free energy change of the reaction, is a function of the entropy changes. What's entropy going to be? Well, we go from some small volume to some larger volume. We saw that as volume increases, entropy increases, and so the entropy change in that expansion will be positive. Entropy change when it moves from a small volume to a larger volume is going to be positive. So this calculation just kind of shows us that the entropy change for that process, the mingling of two ideal gases, it's pretty much the entirety of the delta G. Okay. All right. Sorry, I gotta find my next slide here. All right, so now into that thing that I was going to talk about that I stopped talking about. Something called Raoult's law. So there was a guy named Raoult, and he was interested in what the partial molar Gibbs free energy was of different species in solution. And he knew that that the free energy was a function of the pressure, like we just saw for the gas-based species. And he wanted to see how that energy changed as you went into solution. And so he wanted to figure out what the energy, the partial molar Gibbs free energy was of the species in solution. And so what he did is he started monitoring the vapor pressure above different solutions. And he looked at the pressures present in the vapor above these solutions of each species. And he was doing that so that he could start to talk about what their Gibbs free energy is. So if you imagine that you have some container and it has a solute and a solvent. We're not going to draw the solvent, we're just going to imagine it's there. We're going to draw the solute. Then the solute occupies some fraction of the surface area on the top of this container, and the solvent occupies the other fraction. What Raoult found was that the pressure that is exerted by any component in these systems, for the most part, for most systems, was equal to its mole fraction times the pressure that would be exerted by the pure substance. If you look at this image, you can kind of see why that might be the case. At the surface of this solution, you have a dynamic equilibrium where solvent species and solute species are constantly, because of the internal energy, the internal kinetic energy, being bumped off into the gas phase. At the same time, in the gas phase, we have solute species and solvent species that